Okay, Big O day 2. So a lot of people are kind of at the fuzzy stage. Like, you get that it's got something to do with code efficiency or speed in some sense, and you get that kind of like linear algorithms are better than quadratic algorithms, but like not a lot of detail. So your goal today is like, I'm going to sort of go through the same ideas but in a different way, and hopefully you'll add some detail to this picture, because there's a lot of things in this statement that are like not actually right. Okay, so summary from last time. We had this get largest gap method, which is going to try and find the two elements that are furthest apart from each other, whose values are furthest apart from each other, and return the size of that gap. And so here in this example, the way that we do it is we loop through everything to find the smallest value, and we loop through everything to find the biggest value, and then we return the difference. So we decided that this code was big O of n, which we write this way. But like, what is that actually telling us about this algorithm? So what it's telling us is, as the size of the input array gets longer, the number of steps that this algorithm needs is going to increase not faster than a linear function. That's specifically what big O of n is saying. So think about what that means again. It's not telling us how fast this runs in milliseconds. It's talking about how many simple operations it takes, how many steps it's going to go through before it completes. And it's not actually telling us how many steps it's going to complete for a particular input size. Like, it's not telling me if my array is length 10, it's going to take 500 steps. Instead, it's telling me about how the number of steps is growing as my inputs get larger. And it's telling me, it's putting an upper bound on the growth. So it's not actually saying that it grows like a linear function. It's saying that it doesn't grow faster than a linear function. So it's sort of like a less than or equal to sign. So here are the salient points. The algorithm speed is measured in time steps, and we usually look at the worst case performance for a particular input size. So if the input array was length 10, maybe some arrays that are length 10 would run faster than others. So we're going to look at the array that's length 10 that runs the absolute slowest. And then we're going to look at the array that's length 11 that runs the absolute slowest. And then the array that's length 12 that runs the absolute slowest. And we're interested in the growth for that. The growth for how many steps are required as those worst case performance inputs are getting bigger. And we're not talking about, again, how many time steps it takes for a particular input. We're talking about how quickly that number grows. And again, the growth is an upper bound. We're saying the number of time steps for our algorithm doesn't grow faster than this other thing. So you can think about it as like a rough classification. So we're not saying something very, very specific about your particular algorithm. We're saying your algorithm works more or less like this. So let's go through a couple of the different categories that your algorithm might be. Your algorithm might be constant time. And what that means is that the number of time steps it takes to complete doesn't change regardless of the size of the input. So your input could get bigger and bigger and bigger and bigger, always takes the same amount of time. So in this example, we're just going to sum up the first 100 elements of the array, or if your array is less than length 100, we just return 0. So here, if I give it an array of size 10 or 10 billion, it's going to run in the same number of steps. So that's why it's constant time, because it's not increasing. Linear time algorithms are ones where the number of time steps is not growing faster than a linear function. So checking to see if something contains a value is a good example of this, because you've got to loop over everything once in order to check if a value is there. That's only true of the worst case inputs, though. Because remember, in the worst case, that would be an input where we would have to run the maximum number of time steps for that input. So let's say we've got an input whose size is 100. if I'm searching for a value in a length 100 array, in the worst case, I might not find the value till the end, or maybe it does, or maybe the array doesn't contain the value, and I have to check everything in order to determine that. So the reason we call that a worst case is because you have to loop over everything. So it's going to take the maximum number of time steps. What would a best case look like? Still, the array length is 100, but a particular set of values that represent the best case would be if the thing that we're looking for is right at the beginning. And in that case, we'd exit immediately because we'd find it right away. So for different array lengths, you could always have an array where you only find the thing at the very end, or you could always have an array where you find something at the very beginning. That's possible for all different lengths of array. And so you would say that in the worst case, it's big O of n, because regardless of the size of the array, you have to check everything. But a best case would be constant time, because regardless of the input size, if it is a best case, then I find it right away and exit without looping at all. Big O of n squared is a function, or is an algorithm where the number of time steps grows in proportion to the input size squared, or rather it grows no faster than that. So this is usually representative of code that has nested loops, where each loop visits the entire size of the input. So I thought I'd give you an example that doesn't involve arrays here. We've just got a single integer n. But notice that as n is getting larger, the number of loops is increasing. And so that's what makes it the size of the input. So if you have multiple inputs and you want to know kind of which one is the one that matters, it's usually the one that increases the number of time steps as that input grows. It is possible to have algorithms where you would be looking at two different inputs that each increase the number of time steps. But let's set that aside for the moment. We can come back to that once you've got the basics. So in this example, I'm just displaying a rectangular grid of numbers, and this is going to run in n squared because the outer loop takes n steps, and then for each of those n steps, the inner loop takes n steps. And so this inner system.out.print is going to run n squared times. There are many other possibilities. So there are exponential algorithms, which grow as exponential functions. So if your input goes up by 1, the number of operations might double, or might triple, or might go up by some other constant multiplier. So these are like grossly inefficient algorithms. I don't want to give you a particular example of this one yet. We're going to see good examples of this later on once we study recursion. Logarithmic time. So logs are the inverse of exponentials. So think about how bad it is to have an exponential function. That's how good it is to have a logarithmic function, because logarithmic functions grow very slowly. To be more specific, if the input size doubles, the number of operations might only go up by 1, or might go up by a fixed number. So think about that. You've got an input that's size 1,000, and it takes a certain number of steps. You double it to 2,000, and you only have one more step. You double it again to 4,000, and it's just 2 more steps. You double it again to 8,000, and it's just 3 more steps from the size 1,000. So these are very efficient. Are other families possible? Yeah, absolutely. So you could have n squared log n. You could have things that are more complicated. Somebody asked about 1 over n, and like this has a well-defined meaning. What you're saying is that this family of functions bounds your growth function from above. But it seems to me like this would maybe never happen in practice. You don't want to say never because, of course, there's going to be an example. But I've never seen this happen in practice, because what this is implying is that as the size of your input is getting larger, the number of time steps is approaching 0. It's pretty common to see tables like this, which kind of show all of these different functions together in one table. So constant time and log n grow very slowly. Linear time, n log n squared, and then the other one's over here. This one has color coding where it's indicating that kind of green and yellow are okay, and red is sort of acceptable, and then red is unacceptable. It all depends on your purposes. So I think there's a lot of applications for which n squared is perfectly fine. 2 to the n, realistically, you can't run this on problems that are larger than, a couple of elements. But this is a pretty common way of thinking about the different families. So some people wanted to know, how is this actually used? And one answer is to discuss the trade-offs between different approaches to a problem. And we're actually going to be doing this very soon ourselves, so hopefully you'll get a first-person example of this. But let's say you're familiar with arrays. There are actually lots of different ways to implement something that acts like an array, something where you can access an element or search through it to see if it contains an element. You can insert a value, you can delete a value. So if you look at a whole bunch of different ways of implementing an array, you could compare, what are the different time complexities for the different operations. So for the array that you're familiar with, you can access it in constant time, but it takes linear time to search all the way through it because you have to check every single element. There are other data structures that work like arrays, but you can search them in constant time. It's, no matter how big your array is, it takes the same amount of time to say, does it contain the value 4 if your array is size 10 or if your array is size 1 billion. And that seems very counterintuitive. How could it possibly, you got to check all the things, right? So how could you possibly check 10 billion things in the same amount of time as one thing? And that's part of what makes data structures interesting. You'll get a first-person example of this very soon. But you can start talking about kind of for our particular application, which of these is going to be better. And these are the kinds of planning discussions that you actually have in companies, that you actually have for projects. You'd say, we need something like a list, but for ours, we're only going to add all the data at the very beginning, and then we're only ever going to access the data, and we're never going to add to it again. So in that case, is it going to be better to use an array or a stack? And you can look at the big O to kind of tell you, oh, okay, so arrays take a long time to insert things, but then once it's inserted, you can access them very quickly. But a stack is very quick to add things, but then it's very slow to access them. So if we have an application where we load the data at the beginning, but then we do a lot of accessing of it, maybe it would be better to use an array than a stack, because a stack is going to have very slow access times. So it's for that kind of discussion. You can also use it to compare different approaches to the same problem. So the problem of sorting a list is something that happens a lot in computer science. And there's, dozens and dozens of different approaches to how you can sort a list. So 3 of the most kind of obvious ones that you're going to see at the very beginning are bubble sort, insertion sort, and selection sort. We should pretend that these say O instead of theta and omega. Theta and omega are related to big O, but they mean something slightly different. Yeah, let's just pretend that these all say big O for the moment. Well, I'll tell you about those at a later time. So you think up a sorting algorithm, and then you analyze it, and you say, okay, so in the worst case, it runs as big O of n squared. But then somebody else invents an algorithm, and you're like, oh, theirs runs in big O of n log n. That's better than n squared. It's faster. But that's only in the best case. In the worst case, it's still big O of n squared. And so someone takes your idea and makes another idea that runs in n log n for both the best case and the worst case. So it's a way of sort of keeping track of kind of the relative efficiency of different approaches to the same problem. Okay, let's do some questions and answers. These are your questions. So I don't get best case and worst case. Wouldn't the best case be an array of size 0 or 1, and then it runs in constant time? So this method which finds the largest thing. If you're finding the largest thing, then no matter what, you have to loop over all the elements in an array, which you'd think is big O of n. And in fact, it is. This is a misunderstanding. Yes, if you have an array that doesn't have anything in it, the code will run faster. But the idea is the best case means best case for your particular input size n. So if we're imagining an array that's size 10, think of all the possible arrays I could give it that are all length 10. If any of them runs faster than all the others, then that represents a best case. For find largest, there is no array that's going to run faster than the others, because no matter what, we have to loop through everything. And so what that tells us is that the best case for this particular algorithm is not going to be different than the worst case, because there is no particular input for a given size that would make this run any faster. Somebody says, it seems like big O of n could sometimes be more efficient than n squared. And the answer is absolutely. It's very possible to have a linear function that takes more time steps for smaller inputs than a quadratic function. But the whole point about comparing growth is that even the steepest linear function is eventually going to take less time than even the shallowest quadratic function. So remember that big O is not a statement about speeds for particular inputs. It's about growth. So you can think about it as sort of an end behavior analysis. This is only interesting for larger and larger and larger inputs. So then your next question might be, well, like, why is that useful? Because, like, don't we really just care about the speed for particular inputs? And surprisingly, the answer is no. You know, the reason this is so useful is because very often you do care about the end behavior of your different approaches for things. So, you know, more specifically, you're asking, like, why do we only name the growth family? If our growth function is like 1000n plus 27, doesn't that 1000 matter? Like, why do we still count that as big O of n? So I've got kind of three answers. One is that 1000n plus 27 behaves more like n than it does like n squared. And that's sort of what I mean by, like, linear functions. Like linear growth is more like other linear growth than it is like quadratic growth. So as n gets really large, even though the 1000 does seem like it would matter, 1000n is going to be more like n than it's going to be like n squared. A second kind of answer is, usually it's very fast to tell if something's linear just at a glance, or at a glance you can tell if something's quadratic. It would take more time and effort to be more precise than that, and usually you don't care about being more precise than that. So if you don't care about being more precise, don't take the time to do it. My third answer is, sometimes you actually do care about that 1000. And when you do, then you talk about it and you look at it. So, like, this is a pretty common thing to hear in discussion. Someone might say, hey, both your ideas are big O of n squared, so, like, maybe it doesn't matter. And then someone else would say, yeah, but one of them has a big leading constant. And what she's saying is that even though they're sort of both growing like linear functions, one of them is growing like a faster linear function. So you do actually hear people talk like that. But not all the time. It's only when it's pretty obvious that there's like a huge leading constant for one of them, and it's a situation where it matters. As a little example of why growth is the thing that matters, like, let's pretend that we have an algorithm that draws n boxes, and we're imagining different big O's for different approaches to that algorithm. So if you have a linear time algorithm that draws n boxes, maybe 16 boxes takes 1.6 seconds, and let's wait for my slide to skip there. 1024 boxes takes 1.7 minutes. So going from 16 to 1000 took us from seconds to minutes for a linear time algorithm. What if it's a quadratic algorithm? It's taking us from seconds to days. That's a huge difference, right? And 1024 isn't that big. So that's why it being quadratic rather than linear really matters. And, like, look how good log n is. So going from 16 to 1000 is taking us from less than a second to 1 second. So that's like almost no difference at all. So I think thinking about what these orders of growth mean in terms of actual numbers maybe will make this feel more real to you. Your problems don't have to grow very large before larger orders of growth really make them unmanageable. Several people ask questions like, but what does this actually do for coding? Or like, but what else can this do? What else is this for? And the answer is nothing at all. This is not a technique about coding. This is not a technique that's going to like let you code things faster or better or anything like this. It's a tool that lets you discuss which program ideas are more efficient. But if you actually want to like apply your code to anything in the real world, you're going to need to talk about which approaches are better than which other approaches. And I think that it's significant that you can't do a programming interview without them asking you questions about this. And you can't read a CS book or a CS paper without seeing references to the big O of the algorithms. So the fact that these ideas appear literally everywhere should be a clue to you that something important here is happening. Somebody asks, is it more important that you have clean code or a good big O? And like, usually you don't have to make a trade-off between those two things. You're not forced to. You can do both. Clean code is important if you want to keep working with your code through time, which is basically always, maybe if it's like a one-day school exercise that you know for a fact you're never going to look at again, but exercises that you think you're never going to look at again have a weird way of cropping back up again. And then you want to go back and say, what was that thing that I did? And if your code isn't clean, your old examples aren't going to help you. So I would say clean code is sort of pretty important most of the time. A good time complexity is only important if you need to run your code on big inputs and not have it take forever. And that's important sometimes, but not other times. Okay, that's it for now. I've ignored some people's questions on purpose because I know that we're going to talk about them very soon, and it's going to make more sense when we talk about them in context. So if I didn't answer your question, ask me again, just so I don't forget about it. But believe me, I think the answers will be coming. Other than that, you have a quick programming assignment, and I wish you guys luck.